Hello all, good afternoon. Thank you for coming. So I'm Vishnu Anirudh. I work for an autonomous vehicle startup called Oxbotica. So they make software to make cars self-driving, trucks self-driving, pods, and basically any vehicle. So I'm a data infrastructure engineer for the perception team, which means that I work with a bunch of ML engineers who develop models based on the data that comes out of these cars. While working with them, one of the biggest challenges I observed was tracking data and models. Just imagine, you're working with about 20 ML engineers and you're getting data from different kinds of cars, 10, 15, 20, the number keeps increasing. And the data that you receive is not in megabytes, it goes in gigabytes. And if you lose track of the data, everything becomes complicated. So which is why it inspired me to propose this talk for the conference, because I'm sure you can take this away to your sector as well. If you are from a banking sector or consultancy, or if you're a speech recognition startup. If you're working with ML algorithms and if you're working with big data, I'm sure this kind of philosophy or framework or tool will be useful, which you can apply. So throughout my talk, first I'll be talking about the challenge imposed by the data, and then I'll be talking about the team collaboration in the perception team, the challenges and the requirements. And then I'll be talking about a tool called data version control, which will help us solve the problem or issues we have. And then finally, I'll be presenting you a use case and then taking you through how that use case uses data version control and how in the end all the issues are mitigated. And at the end, I'll take questions if you have any. So this is a car that's being developed by Oxbotica. It's a self-driving car, and there are lots of sensors on that. But there are three main categories of data that come out of that. The first one, it's the camera feed. There are about 4 to 5 cameras there. And in fact, in a minute, you get about thousands and thousands of images. And then you get data of the LiDAR sensor, which is a laser-based scan. So you get lots of laser-based LiDAR scans. And also, just below the number recognition plate, there is a radar embedded, so you also get the radar data. So this is what constitutes a self-driving vehicle, in a self-driving car particularly. So can anyone in the audience just guess how much data is generated out of this car?
Unit, what's it?
Doesn't matter. You choose the unit, you choose the number. Anything, even random guess is fine.
5 terabytes an hour.
Yeah, good. Any?
Lower.
Yeah, nice. Yeah. So initially, it used to be around 10 terabytes for a few hours. But nowadays, because they have applied so many compression algorithms inside, the data generated is 4 terabytes per car per day. So just imagine 4 terabytes per car per day. And we are a startup and we plan to grow, and just imagine the amount of data that we'll be getting from vehicles. Just to put the issue in perspective, so we have cars that have been added to our fleet every day, and we just don't aim to make cars self-driving. We aim to make trucks, pods, ships, any vehicle self-driving. And when you run them for days, months, years, there's so much data is going to be collected. In fact, there is going to be an exponential explosion of data, and there is a serious need to kind of know where the data is coming from. Now this is on the field, on the front end. Now let's see what happens in the back, in the office. So I'm working with the perception team, which means there are a bunch of machine learning engineers, and each of the engineer works on different aspects of a model. So all of them don't work on a single model. For example, one engineer might be working on, let's say, vision data, another engineer might be working on radar data, and another engineer might be working on optimizing the issue. So maybe the accuracy was 88%, he wants to increase it to 95%. That's a lot of work involved. But the key issue is that the models, all of them they're working on, they're very independent. So they cannot just go, okay, I'm going away for a sprint, I'll just work on my own and come back. That's not going to happen, because each model is interdependent on each other. So to develop models, like to develop robust machine learning models, you need like good data, clean data. So that's a major requirement of the team. Just imagine if you have corrupted data, this is going to affect the model which will be running on the cars. So in the end, the performance of the cars won't be as expected. So they need to collaborate with data labelers. Now, data labelers can be a person working full-time just labeling data, or it can be a machine learning engineer who is labeling data for the given sprint. So what these data labelers do is that, let's imagine the images that come from camera frame. So they kind of say, okay, I have this image, now this is a pedestrian, this is a road, this is an object. So they label each and every pixel and classify them according to the label that are there. So in effect, the machine learning model, when it goes through the images, it will see, okay, so this is a pixel, this is how an object looks like, this is how a pedestrian looks like, and it trains on them. So the need to collaborate with data labelers is really important. And data labelers, they might be an entire team sitting there. So you need to know where the data is coming from. And finally, you need to easily track data. They need to know, okay, who worked on that, what changes to data were made. Now imagine this is a safety critical system. This is going on actual cars and vehicles. So it is very important to know the history of the data development. So in a sense, there is a very important need to track data and models. So, which is why I will take you to data version control, or DVC. DVC is a Python library, so if you want to get started, you can just do pip install DVC, and they cater to different OS as well, and it's an upcoming project. So it's basically a version control system for ML projects. It tracks ML models and datasets like Git. In essence, it's like Git for data, but it does much more than that. It runs on top of Git repository, so it goes hand in hand with any Git repository. And most importantly, it runs a full ML pipeline. So you have the data, you have the algorithm. Now you need to run the pipeline, and DVC will help you do that. And if you have developed a model in the past and you want to just check it out, DVC will help you to reproduce the entire experiment as well. So in essence, it's Git for data plus running your ML pipelines. Now let me take you through a use case. Now we have a data labeler, and he produces a labeled data, keeps producing labeled data, uploads it in the cloud. And there is an ML engineer who pulls the data from the cloud, and he works on that. His specific interest is to use vision data and develop the model. Now there is another ML engineer who wants to use the radar data. Now she wants to build on top of the model developed by her colleague. So their models are interdependent and they need to collaborate as well. Now let's see how the data labeler would use DVC. So the data labeler, after he's done labeling the data, he uploads it to a folder called, let's call it data underscore folder. We'll see why this name is important because it will be used throughout. And to kind of add to DVC, he just says DVC add data underscore folder. So this is basically saying that, okay, here DVC, here's my folder, just make sure that this is tracked. And then DVC produces a .dvc file. I'll come back to this later, how it produces. But what the data labeler does is now he puts that into Git. So he says git add this DVC file. And with that, he also adds a .gitignore file. I'll again come back why he's doing that. And then at the end, he commits. So there is a commit created that the data has been generated. And in the end, he pushes it to the remote repository in Git and remote storage in wherever he wants to store, whether it's AWS S3, Google Compute Cloud, or Azure, or any network attached storage. So let's go a bit deeper. So when the data labeler does DVC add the folder name, so what DVC does is it adds the folder to a local cache according to its format. And then it adds the name of the folder to .gitignore. So this is basically DVC saying to Git that, hey Git, I have this data, but you don't have to track the entire data set. You just know that there is a file generated, so I'll track the data for you, and you just make sure that you track the .dvc file that I generate. So when you add to .gitignore, Git doesn't track any of the data, but it tracks .dvc file. And just to kind of give you an idea how a DVC file looks, it's basically a bunch of metadata, like whether you need to have metrics, or you have the author's information, name, email address. It's not really important right now. So in essence, there is a .dvc file generated, but the data itself is not tracked by Git because it's already being tracked by DVC. Now next, Git adds the .dvc file to the repo, and the data itself is not tracked. So if you have like 10 gigabytes of data, you won't see each and every individual file in Git, but you just see that it's .dvc. So if you go to a Git repository and say data.dvc, then you'll know, oh, there's a data there. So I'll just check out how it looks. And then you push it to the remote repositories. Now for DVC push, the data is pushed to a remote storage. So DVC is storage agnostic. So it means that you can push it to any network attached storage. And then because .dvc and .gitignore files are pushed, the data is not tracked, and you know that there is a DVC file, so there should be a data. And DVC is compatible with any standard Git server or provider, so you can start using it straight away. Now, the data labeler has done producing a labeled data. Now the ML engineer needs to pull the data and work on that. So what the ML engineer does is he clones to the Git project, so it sees a .gitignore and a .dvc file. So it pulls the data. So all he has to do is DVC pull data underscore folder .dvc. So he doesn't have to bother about going to Google Drive and going to this particular folder and copying the data. Just one line command, and the data is in your local machine in a few minutes or a few seconds. And then after that, the machine learning engineer, he has a model, a Python file that he wants to train with this data and see how it looks. So he does DBC Run with some parameters. And finally, he pushes the changes to the cloud, like we saw previously. Now let's see what these parameters are when you run the machine learning experiment. So DBC Run basically builds a dependency graph using the dependencies and the outputs. So a standard command would look like something like this. So when you say DBC run, you want to execute the final line. So Python, this machine learning code with this data folder. But DBC needs to know what each file is. So you say the top two are dependencies. So now DBC can track, okay, so these two are dependency. I'll be mindful of that. And then next one is output. So at the end of completion, it gets stored over there. So DBC knows, okay, this is the output. I know I'll do kind of the things that needs to be done with an output. And finally, the code saves the metrics to an eval.json file. So DBC knows that if you need to get any metrics, like if you want to publish to your logs or Grafana, DBC knows where to get the information from. And finally, now this is a dependency graph. So at the end, it gets stored to a file. You can specify the name of the file to be train.dbc. So this will be used later on, so just be mindful. So this dependency graph gets stored to a file called train.dbc. Now this ML engineer runs the experiment, pushes the changes to the remote Git repository and the remote storage. Now let's see what the other ML engineer does. So this ML engineer wants to train on top of the radar data, but she needs to build on top of the code developed by her colleague. Now she goes to the Git repository, clones it, and then she pulls the data, dbc pull data underscore folder.dbc. Now she has data in a machine. So first she does dbc repro. So she wants to reproduce the experiment done by her colleague. And then she wants to see what is the accuracy. So she just says dbc metrics show. So all of these commands are kind of intuitive, and for users who use Git already, this you can get started right away. And at the end, she builds on top of train.py, the Python file for the machine learning code. She includes code to train on top of radar data, and she runs her experiment again using the command DBC Run. So let's see what happens in a DBC repro file. Now remember that previously we ran as DBC Run with a set of parameters. So what repro does is it reruns this graph again. So it restores the dependency graph. And when the ML engineer enters DBC metrics show, it just brings out the metrics that's there in a JSON file. So you don't have to kind of figure out what file is what. You just access it via the DBC client interface. Now, just to recap, we have our data labeler who in Git repository, he checks in, he kind of commits a .dbc file. Now, both the engineers know that there is a data sitting there, so they clone the repo, and then they do dbc pull. And now the ML engineer who is working on vision data, he kind of creates a version of train.py. So here a train.dbc file is created, then he checks into Git. Then again the other ML engineer, she kind of checks out the commit A, and then she updates train.py, so train.dbc file is updated. Now again, the ML engineer using vision data, he realizes that, okay, this data needs updating. There are some config files that need to be added to this, so I'll update the data folder. So he updates the data underscore folder.dbc. And finally, the ML engineer using the vision data, he wants to fine tune the model. So he updates the train.py and updates train.dbc. Now, the other ML engineer, she wants to just check out how things are going on and she heard from a colleague that the performance has increased. So she checks out to commit D and then does DBC repro. Then she realizes that, oh crap, the accuracy has gone down to 68%. Now let me just go a step back. So she commits to commit C, and then she runs repro again. She sees that the accuracy hasn't changed much, so she realizes that, okay, so this commit is not helping, so I need to go to a previous commit and see. And then she goes to commit B, and then she realizes, okay, so now things have come back to normal. It was 91 to 92%. Now there is some problem in commit C, and then it becomes easy for her to debug. Now imagine if DBC wasn't there, and we had the traditional approach of copy-paste the data. So each data is like, let's say, 20 gig, and you have about 100 data sets. It really becomes difficult if your models fail, or if it deteriorates because of some change in data. And this is just a scenario with one data labeler and two machine learning engineers. In normal setting, like I worked with about 20 ML engineers, and there are about 5 to 6 data labelers, and as we grow, there will be more and more people coming in. So there is a clear need for tracking data and models, and so that you can see how they have been developed. And also, when they go into safety critical systems, like vehicles or even spaceships, rockets, you need to kind of prove that you need to be it needs to be foolproof. So you should be able to show that, here, look, the data, there is no problem with that, everything is fine. So whatever clearance you want to give, you can go ahead and give me. So yeah, this is how a version control system for data would look like, and it becomes easier for developers as well because they can go hand in hand with Git and DBC. So it helps you to get started right away. And yeah, so this is an upcoming project. Even I realized this a few months ago, and ever since I've been contributing to it. So if you want to do anything, feel free with this. Thank you very much.
Thank you very much. Is there any questions for Vishnu? And just a reminder that questions are questions.
Right.
Hello, thank you very much for the talk. So the question is that in a couple of hours in the very same room there's going to be another talk which is called Hanger about Git for your data.
Yeah.
And from the quick description provided, it sounds very similar to what you have just explained.
Yeah.
So if it's right to assume that these are similar solutions, then can you maybe quickly give a comparison between the two if you have worked with Hanger, and what to pay attention to on the next talk, and what are the differences?
To be honest, just today I saw about Hanger, so I haven't tried that. If it's another solution like GitHub and Bitbucket, it's great. But when I had a brief look, I wasn't sure if it caters for machine learning algorithms as well, which is another important aspect other than versioning data. So yeah, I think it's about what kind of suits you. If you just want to track, and if DBC doesn't add, then Hanger might be a good solution for that, or vice versa.
Thank you.
Thanks for the good talk. One question I have is what sort of infrastructure do your engineers use behind the scenes? Are they all got individual machines, or using a central cluster? And if so, are you copying all these big data sets locally every time you do a pull in DBC?
So at the moment, our engineers, they use their individual machines or laptops. So at a time, they need to kind of work on data sets that's worth 10 GB or 20 GB. So they just go to the repo, they just locate the DBC file or the data set they want to work on, and they just pull and start working on that. But eventually, as it grows, there is an idea that we start using clusters. So there is no kind of pulling it to your machine at all. There is a remote cluster, and you kind of go to the remote cluster that sits in office near a desk maybe. You just go there and get the data, and work with it and see how it is. But at the moment, it's individual machines.
Come around.
Do the data labelers label effectively annotate raw data, or do they? So the annotate raw data is not like there's data that's cleaned and then given to the labelers, and therefore you have to go back to the raw data. They are annotating on top of raw data, so that's
No. So the data comes from the car, and then so they don't annotate all of the data. So there are some snippets that are taken, which are of interest for the models. So we just ignore the other data which have been trained previously or it's not very useful. So we first take snippets and then we give them to the data labelers.
And so they never need to refer back to the raw data that came from the car?
No. They just work on the snippets, yeah.
Is there any kind of conflict resolution stuff built into DBC? Because that's one of the most painful parts to get for me.
Conflict resolution, as in you have two different types of data in the same folder?
Sort of when two people have been working on the same bit of data and then they both try to check that in at the same time. Is that something that is handled by DBC? Is that an issue for them?
Yeah.
So?
So let's imagine there are two people. So one person checks in his data and the other person checks in her data. Now there are two different kinds of DBC files. So the DBC tracks based on that. So when you merge, like git merge, you need to kind of sit together and talk what's useful, what's not useful, and then create a common DBC file.
Sorry, could you give an example?
Can I ask you to speak into the mic? Sorry. Just so the camera can see the recording.
Could you give an example about the use case of the data version? So because my understanding is like labeled data.
Yeah.
And because in machine learning algorithm you need to random choose. So probably for the new version actually it's just adding more rows.
Yeah.
Real data. Is that the same case?
Yes. So you have a data.dbc file and you want to add in more data, so you just update the data set and the DBC file gets updated eventually. And in Git you see that how you have developed the data, what are the additions you have made.
If there are no further questions, let's thank Vishnu for very interesting.